Bismillahirrahmanirrahim. Assalamu alaikum. Let's continue the techniques of stochastic integration further. Recall, if a function is depending on time and also Brownian, then for this kind of function, we have seen that differential is given by df is partial derivative of f with respect to s plus uh, 1 half second partial derivative of f with respect to the Brownian. So it's t basically dt plus partial derivative of f with respect to Brownian d Brownian. So if you want to use s in place of t, you can also use that. Because I was using in the previous video, that's why in the start I was using s. Okay, so you need to recall this, right? And one more thing is, you can rearrange this, but first you can integrate and rearrange, then you can get what you can get. So integral from 0 to t, let's say df to be 0 to t partial derivative of f with s plus 1 half second partial derivative of f with respect to Brownian ds plus partial second of f with s with Brownian d Brownian, right? Now this is what that we will be interested in most of the time. So if we have a function, like I can write this 0 to t partial derivative of f with respect to Brownian. It is in the usual sense, so it is differentiation in the calculus 1 sense. You can say that 0 to t df minus 0 to t partial derivative of f with s plus 1 half second partial derivative of f with respect to Brownian and ds, right? So we will make use of this formula for solving certain stochastic integrals. So now I will bring a question, like I write an example which we will be solving using this version of Ito Lemma. Okay, we want to calculate this integral, so we want to see to which expression this stochastic integral is equal. So what we have to do is basically we have to compare this quantity over here with this. Then we will need a function. So we need a function f for which the partial derivative with respect to w in the calculus 1 sense is equal to this quantity, which is e to the s by 2 cos w's of s, right? So I need a function whose uh, first partial derivative with respect to w is this guy over here. So how can I get such f? So you can integrate in the calculus 1 sense. So it is going to be f equal to, so you have to integrate with respect to dw's of s on this side. So you will get what you will get, e to the s by 2 will remain same. So it's kind of integrating with respect to w sub s, so it is going to be sine w sub s. So now this is going to be my function over which I will apply the Ito lemma that I have recently stated in this form, right? First I will do what I will apply Ito lemma on this, and then I will integrate on both sides, and ultimately I will get to this stochastic integral. So I need what for this f? I need quite a few things. First I need its derivative partial with respect to s, which is going to be s by 2 e to the s by 2, so 1 by 2 e to the s by 2 sine w sub s, right? And what more I need? So I need partial derivative of f with respect to s, rt, you can say no problem at all. And I need second partial derivative with respect to w. Of course I also need first partial derivative of f with respect to w in the calculus 1 sense, so like in the usual sense of differentiation. So let's differentiate with respect to Brownian rw first. So it is going to be e to the s by 2, so you have to differentiate only with respect to w. It is going to be cos of w sub s, and when you differentiate it again for the second derivative case, you will get minus e to the s by 2 sine of w of s. So now you have got the partial derivative of f with respect to s, partial derivative of f with respect to w, and second partial derivative of f with respect to w. Now your task is to go to apply the Ito lemma, which is in this form, df to be partial derivative f with s plus 1 half second partial derivative of f with respect to w, and ds plus what I have to write here is partial derivative of f with respect to w dw sub. So you can use s and t are interchangeable, and interchangeable. You can use srt, no problem at all. So my df, so my f is e to the s by 2 sine w sub s, which is equal to, so partial derivative of f with respect to s we have calculated, it was 1 half e to the s by 2 and multiply by sine of w's of s and plus 1 half, and second partial derivative of f uh, turned out to be minus times s by 2 sine w's of s. We have calculated about over here, so it is here, right? Then plus partial derivative of f with respect to w, which is going to be e to the s by 2 cos of w sub s dw sub s, right? But you can see that this is half of e to the s by 2 times sine w sub s, and it is minus half of e to the s by 2 times sine of w sub s. So this gets cancelled with each other, and ultimately we get the differential of e to the s by 2 sine w sub s to be equal to e to the s by 2 cos w sub s dw sub s. So now you can integrate from 0 to t. The reason why I was using the s, because I had to integrate at last from 0 to t, so that the integral should make sense, 0 to t. Okay, and then what can I do now? So like it is the differential of f, so d and integral, they uh, cancel each other in rough sense, so it is going to be e to the t by 2 sine w sub t minus e to the now 0 by 2 sine w sub 0, right, equal to 0 to t e to the s by 2 cos of w sub s dw sub s. So now what can we conclude from here? So like, because w sub s is 0 and sine of 0 is 0, so this is going to be 0. So the integral from 0 to t of e to the s by 2 times cos of w sub s with respect to Brownian is going to be e to the t by 2 times sine w sub t. So this is the integral. Of course, stochastic integral that we solved using the technique of Ito Lemma. Let's evaluate one more stochastic integral, and this time we have this stochastic integral of exponential of Brownian minus s by 2. So what we will do now, so by the same trick, we need f whose partial derivative with respect to w is e to the w minus s by 2. So I need a function. In other words, for this, finding f over this process, I will be, like using the usual calculus. So like I need f, for the f I need to integrate. So it is, rough. It's not, a standard part of this. So all that I have to do, the trick that is going to work is going to be, I have to find f. So I need an f, suitable f, over which I will apply the Ito lemma. And fortunately, that f, you know uh, can be found by this finding out of antiderivative strategy. So the f is going to be equal to e to the minus s by 2 can be taken as common, e to the w dw, and which is going to be same, like uh, because each exponential has the same integral, so w minus s by 2. So luckily in this case, our f is going to be the same as it is given inside the integral. So I will consider my f of s comma w sub s as e to the w sub s minus s by 2. Now what I need for applying the Ito lemma are the three things, and these are partial derivative of f with respect to s, partial derivative of f with respect to w, and second partial derivative of f with respect to w. So first I will find out its first partial derivative with respect to s, and it is going to be minus 1 half e to the w sub s minus s by 2. And then I need its partial derivative with respect to w, which is going to be of course the same, like e to the w sub s minus s by 2. Of course second partial derivative will also remain the same, which is going to be uh, e to the w sub s minus s by 2. Some book use b sub s for w sub s, so this is just a convention. So now I will use the formula, and it says that the differential of f is given by partial derivative of f with s plus second partial derivative of f with respect to w half, basically ds, plus first partial derivative of w with s dw, right? So my df or d e to the w sub s minus s by 2 is equal to partial derivative of f with respect to s, which is going to be minus 1 half e to the w sub s minus s by 2 plus 1 half second partial derivative, which is going with respect to w, which is going to be w minus s by 2 ds plus partial derivative of f with respect to w sub s, which is going to be e to the w sub s minus s by 2 dw sub s. So it is 0 because minus half and plus half of expressions are going to be cancelled out. So we will be left with the differential of e to the w sub s minus s by 2, same as e to the w sub s minus s by 2 with respect to dw. If you integrate from 0 to t on both sides, so you will be left with this. So it is going to be e to the w sub t minus t by 2 and minus e to the w sub 0 minus 0 by 2 equal to 0 to t integral of e to the w sub s minus s by 2 dw sub s. So then this e to the 0 is going to be 1 because Brownian at 0 is also 0, so e to the 0 is 1, and hence your integral 0 to t is of this exponential of Brownian minus s by 2 with respect to Brownian is going to be equal to e to the Brownian minus uh, t by 2 minus 1. So this is the answer to the stochastic integral that we were interested in. Thank you. In the next videos we will move towards doing some other crazy techniques of stochastic integration.